Welcome to Mrs. Lee's Chemistry Academy. Today we're going to focus on the type of solid. This is tied to the several learning objectives from the College Board. That the student can create visual representations of ionic, metallic, network covalent, and molecular solids to show characteristics of their structures and interactions present. That the student is able to explain a representation model that connects properties of ionic, metallic, network covalent, and molecular solids to their structural attributes and to the interactions present at the atomic levels. That the student is able to design or evaluate a plan to collect and or interpret data needed to deduce the type of bonding in a sample of solid. And able to compare the properties of metal alloys with their constituent elements to determine if an alloy has formed, identify the type of alloy formed, and explain the differences in properties using particulate level reasoning. There are three types of crystalline solids. One being molecular solids composed of individual molecules such as water or carbon dioxide, dry ice. Secondly, the ionic solid composed of molecular units, cations and anions such as sodium chloride, silver chloride, magnesium oxide, barium sulfate, etc. The third type are ionic solids, out of which first, non-bonding. These are noble gases held by London dispersion forces such as argon and xenon. Metallic, meaning like sodium, copper, silver, these metals, and we use the electron C model to account for their properties. And network covalent such as diamond, graphite, silicon dioxide. Here we need to make a differentiation between intermolecular force and intramolecular bonding. Intermolecular force refers to attraction between individual discrete molecules that hold them together as solid, liquid, or gas. But intramolecular bonding refers to the bond that holds units together to form macromolecules with lattice arrangements. Here is a chart that would help us to understand the different kinds of solids and whether they operate by intermolecular force or intramolecular bonding. Starting off with the crystalline solid at top is subdivided into atomic, ionic, and molecular solids. In terms of ionic solids, we are further subdivided into three types. We have the non-bonding solid like xenon that operates by IMF. And then we have the metallic bonding like copper, and we refer to as intramolecular bonding. Then we have the network covalent, which is the diamond, graphite, and silicon dioxide, referred as intramolecular bonding. And then we have another category, ionic solids, like sodium chloride, intramolecular bonding. And finally, the molecular solid, like ice with intermolecular force. First, molecular solids. They consist of nonmetals, diatomic elements, or compounds formed between nonmetals. They are composed of individual molecules held together by weak intermolecular force such as LDF, dipole-dipole forces, and hydrogen bonding. They are like sucrose, ice, or dry ice. They have low melting point due to weak intermolecular force. And they do not conduct electricity because electrons are tightly held within the covalent bonds. Sometimes they are composed of large biological molecules or polymers. This is a diagram of molecular solid of ice. It is formed in lattice regular hexagonal arrangements with extensive hydrogen bonding, and the volume is expanded so that ice is less dense than water and be able to flow on water. The second type is ionic solids such as sodium chloride, table salt. Now, they are crystalline solids in regular three-dimensional lattice arrangement formed by strong Coulombic interaction between cations and anions, which we call the electrostatic force of attraction. The higher charges and smaller distances between ion centers will increase the Coulombic force of attraction, forming solids with higher melting point and boiling point. As we have mentioned earlier, that ionic solids are very soluble in water, and therefore when they are dissolved in water, you have this ion dipole attraction. Ions become separated, surrounded by water molecules. Ionic solid also exhibit low vapor pressure due to strong ionic bonding. They will conduct electricity when the ions are separated, either in the molten form, meaning when they are melted, or in aqueous solution when dissolved in water. They are insoluble in nonpolar solvent because the attraction between ions are much stronger than the attraction between the separated ions and nonpolar solvent molecules. Ionic solid is brittle, and here's a diagram that can explain why. Before the displacement, we have very orderly arrangement of alternate positive negative charges to hold them together. However, when the layers are displaced, then we have positive charges together and negative charges together, and that creates repulsion. Therefore, ionic solid is brittle after being displaced. Practice problem number 1. Use the ionic radius in the table below for the different ions to account for the relative melting point of ionic solids. And the ionic solids are sodium fluoride, potassium fluoride, magnesium oxide, and magnesium sulfide with their melting point given in the table. So here, really, we have to pay attention to the charge of the ions and the size of the ions. The greater the charge, the greater the attraction in the Coulombic force between the opposite charges. The smaller the ion, also the greater the attraction in terms of the Coulombic force of attraction. Therefore, we understand that the greater the Coulombic force, the higher is the melting point, and therefore we can rank them in this order: potassium fluoride, less than sodium fluoride, less than magnesium sulfide, and to top it all is magnesium oxide because of the higher charge and the smaller distance. Category 3A, non-bonding atomic solids. They are solids of noble gases, such as argon, krypton, and xenon. They are held together by very weak London dispersion forces, and they have very low melting point because of the weak LDF, and their melting point are in the negative region. 3B, metallic solids. We are using the electron C model to explain the metallic solid bonding. It is represented by positive cores, which include the nuclei and the inner electrons, surrounded by a sea of delocalized mobile electrons. And the bonding is non-directional. So these little green things that you see are the valence electrons that move around. And that would give rise to the properties of metallic solid being shiny, because when light comes in and hits one of the delocalized electrons, light will get deflected back to make it shiny. Metals are malleable and ductile because the surrounding environment of the metal cores is not changed when metal is deformed. And they're good conductor of electricity and heat because delocalized electrons are free to move. And they have a range of melting points, such as the fact that cesium melts in your hand. When we put metals together to make a homogeneous mixture, we create alloys. And there are two kinds. One being interstitial alloy, such as steel. It is formed by filling these little spaces between the large iron atom and fill it up with smaller carbon atoms. Atoms are prevented from slipping across each other, therefore we have more rigid lattice yielding a stronger alloy in steel. And oftentimes we add chromium atoms to the surface to form a non-reactive chromium oxide layer when exposed to air. In other words, the air will oxidize the chromium, and this will prevent the oxidation of the iron atoms underneath. So here's a picture of the interstitial alloy of steel with iron, and inserted in between the empty spaces are small carbon atoms that would give it the strength and rigidity. The second type of alloy is substitutional alloy, and it's formed by substituting some atom with other atoms of comparable radius to change the alloy density to between that of the components. Such as brass is formed by replacing some copper with zinc. An alloy remains malleable and ductile. So here's a diagram of the substitutional alloy. Copper is red and zinc is gray. So some of the copper atoms are replaced by zinc atoms of similar size. Pewter is a malleable alloy made from 98% tin and 2% copper, and cast iron pan is hard and brittle alloy made from iron and 2 to 5% carbon. Use information from the table below to explain the choice of metals to yield specific properties in the alloy. Now, in the metallic radius, you see that tin and copper are similar in size. Carbon is much smaller. Melting point, however, is very high in carbon, quite high in copper and iron, but very low in tin, relatively speaking. Well, tin and copper atoms have similar radii. So if you make a soft substitutional alloy, you can put in small amounts of copper to replace the tin atoms. Copper, due to its high melting point, is added as a hardener to the low melting tin so that malleability of the alloy is still maintained and pewter can be handcrafted beautifully. And then when you insert the smaller carbon atom into the vacant spaces between larger iron atom to form interstitial alloy, the high melting carbon increases the hardness and the non-malleability of cast iron pan to be used as a cookware at very high temperatures. The next category are covalent network solids. And it can be separated into two-dimensional or three-dimensional network formed from the carbon group due to its ability to form 4 covalent bonds. The network of carbon are diamond, graphite, buckyball. And the network of silicon are carbon dioxide or silicon carbide. Let's take a look at diamond. Now, diamond is a three-dimensional network formed by carbon atom covalently bonded to 4 other atoms. It is tetrahedrally bonded with a geometry of 109.5 degree bond angle coming out from sp3 orbital hybridization. It is rigid and hard because covalent bond angles are fixed and can be used as abrasive for industrial cutting. Has very high melting point, 3,800 degrees C, insoluble in any solvent, and is an insulator that does not conduct electricity. So here's a diagram of carbon. Of diamond. Notice how the carbon atom is tetrahedrally bonded in three-dimensional network, giving it very high melting point and very, very strong. Now, in terms of graphite, it is a two-dimensional network, also made of carbon atom, and it will be fused and arranged in a six-member rings. Each carbon atom in the layer forms sigma bond with 3 other carbon atoms. And therefore it gives trigonal planar geometry and bond angle 120 from the sp2 orbital hybridization. It has high melting point because of the strong covalent bonds. But the unhybridized 2p orbitals perpendicular to the plane combine to form pi bonds with delocalized electrons that contributes to the stability of graphite and the electrical conductivity because the electron can travel now between the layers through the 2p orbital. And the layers are connected by weak London dispersion forces, so the layers can slide past each other. Therefore, graphite is soft and slippery, and we can use it as a lubricant. So here's a diagram of the graphite. Notice that there are layers of these 6-member rings, and then between the layers are connected by the weak p orbital, allowing electrons to go through to conduct electricity, and the layers can slide past each other, giving it the softness as a lubricant. Now, silicon dioxide, silicate with an empirical formula of SiO2 are extended arrays of silicon and oxygen in three-dimensional network. Quartz made up of network of SiO4 tetrahedra with shared oxygen atoms. When quartz is heated above the melting point of 1600 degrees C and cooled rapidly, irregular structure of amorphous glass is formed. And silicon's conductivity increases as temperature increases. So here's a diagram of the silicate. As you can see, each central silicon atom is bonded to 4 other oxygen atoms, and 2 of which they come from another silicon dioxide. Semiconductors. Silicon can be doped with 1 extra valence electron, like phosphorus or arsenic, to convert it into negative charge carrying semiconducting material. And silicon can also be doped with 1 less valence electron, boron, to convert it into positive type semiconducting material. The junctions between the N-doped and the P-doped material can be used to control electron flow in modern day electronics. Here's a diagram. As you can see on the left-hand side, we are doping the silicon with arsenic atom, which has an extra electron. And on the right-hand side, we are doping the silicon material with boron atom, which has 1 less electron, therefore creating a hole. And when you put these 2 together, it creates electron jumps, which then allows for electron flow in electronics. Problem 3. Now this is related to a lab that you might have done to determine intermolecular force or intramolecular bonding based on a set of properties. There are 5 solids A, B, C, D, and E. And they are glucose, iodine, potassium nitrate, silicon dioxide, and zinc in no particular order. And we come up with the following properties. First, we describe their appearance, and then solubility in water, and solubility in hexane, the nonpolar solvent, their melting point being low or high or very high, and the electrical conductivity, whether it conducts in pure phase or it has to be dissolved or melted or in aqueous solution or doesn't conduct at all. And of course, going back to the melting point, being in thousands cannot be done in a laboratory. So we just say, we look it up in the from other information, but we also rank them as low or high or very high. So substance A is identified as glucose. The reason is it has low melting point, it is soluble in water, and it does not conduct electricity. It is a molecular solid with hydrogen bonding, dipole-dipole, and LDF. Substance B is identified as silicon dioxide because it has very high melting point, insoluble in solvents, and no electrical conductivity. So the type of solid is network covalent. Substance C is identified as zinc. This is atomic solid due to metallic bonding. It has high melting point, insoluble in solvent, but does conduct electricity, and that gives you the clue to identify as a metal. Substance D is potassium nitrate, ionic bonding. It has high melting point, soluble in water, conduct electricity in aqueous solution, and there's your clue that it is ionic, because only ionic solid will be soluble in water to form ions to conduct electricity. And then the last one, E, is iodine. It is molecular with London dispersion force with low melting point and soluble in hexane, the nonpolar solvent, and does not conduct electricity. To summarize what we have learned today, we learned how to classify various types of solids. We used representation and structure of molecular solid, ionic, metallic solid, and network covalent to account for their properties and interaction at the atomic or molecular level. We use particulate reasoning to explain differences in properties between substitutional and interstitial alloys. And we noted the difference between positive type and negative type semiconductors. And we also interpreted the lab data of an intermolecular force lab to identify solids and deduce the type of bonding. From the team of MLCA, we would like to thank you for watching our video, and we hope to see you again.